Welcome back, everybody. In this video, we're going to start working on section 3.6, which is about real zeros of polynomial functions. And so basically what this is about is this. You know from your earlier work that any quadratic equation, you can find the two solutions of it using a variety of methods, one of which we know is the quadratic formula. And the thing is that every quadratic equation has two solutions, and this formula will find it for you. Of course, a linear equation is much easier to find the solutions for, but it's doable. This section is about how can we find solutions of equations that have higher degree. Like what if it is x cubed or x to the fourth power and so on. So how do you find solutions to all of these equations? This section is more theoretical than the last couple of sections we've had and is also kind of longer. So we'll have to be kind of careful going through it, but we'll also be giving a lot of examples throughout to help make the concepts clearer. Okay, so let's go ahead and get started by taking a look at the remainder theorem. So a theorem in math, by the way, is basically just a usually important rule or fact about something. And so that's what this is. It's the remainder theorem. And it says if you have a polynomial f of x, and it's divided by a linear factor of x minus k, then the remainder is the value f of k. So we want to see how that works with an example. So we're going to divide x squared minus x plus 3 by x minus 2. And fortunately, this is a good chance for us to practice with synthetic division. So our divisor was x minus 2, so we'll have positive 2 in the little box. It was 1x squared minus 1x plus 3. The 1 will drop straight down. Now, to do the division, recall that for synthetic division, it was a repeated multiply and add procedure. So we'll have 2 times 1 is 2. Negative 1 plus 2 is 1. 2 times 1 is 2. And then 3 plus 2 is 5. Okay. So then the final answer is going to be x plus 1 plus 5 over x minus 2. All right, so that's what we get when we divide. Okay, part B, let's find f of 2. F of 2 will be 2 squared minus 2 plus 3. That's 4 minus 2 plus 3. 4 minus 2 is 2. 2 plus 3 is 5. All right, so what the remainder theorem says is the fact that we got a 5 right now, and the remainder on the division turned out to be a 5, it says that's not an accident, okay? If you are dividing by x minus k, the remainder that you get is going to be f of k, okay? And that's the remainder theorem, okay? So let's try that another example. So here it says use synthetic division and the remainder theorem to evaluate p of c. So here we're going to do number 40. Here our c is 1/2, okay? So we would be dividing by x minus 1/2. So we will have 1/2 in the little box. It's 2x squareds, 9x's, and 1. The 2 will drop straight down. Repeated multiply and add procedure. 1/2 times 2 is 1. 9 plus 1 is 10. 1/2 of 10 is 5. 1 plus 5 is 6. So then our answer here is going to be 6. Okay, if you like, you can check separately and find out what p of 1/2 is by directly substituting. 2 times 1/2 squared plus 9 times 1/2 plus 1. So let's go ahead and do that. Okay, so 1/2 squared is 1/4. 2 times 1/4 is 1/2. 9 times 1/2 is 9/2. 1/2 plus 9/2 is 10/2. 10/2 is 5. 5 plus 1 is 6. All right, so once again, the remainder theorem is telling us that the fact that those two were both 6 is not accidental. Okay, a second and also important theorem we have from this section is the factor theorem, which is next. We've actually already kind of used the factor theorem before, but we may not have called it that, and that's okay. The factor theorem goes like this. K is a 0 of f of x if and only if x minus k is a factor of f of x. So recall that a 0 of f of x is a number c such that when you substitute c into the function, you get 0. So if c is a 0, then f of c will equal 0. What this says is that k is a 0 of the function if and only if, this is the condition goes both ways, if and only if x minus k is a factor of f of x. Okay, so here it says let p of x equal x squared minus 7x plus 12. We're going to first find p of 3, and then we'll factor p of x. Okay, so p of 3 first. So that will be 3 squared minus 7 times 3 plus 12. 3 squared is 9. 9 minus 21 plus 12. Okay, 9 minus 21 is negative 13. Nope, it should be negative 9 minus 21 plus 12. Okay, so I'm going to reorder these because I can't remember how to do 9 minus 21 easily for a moment. So I'm going to add together the two positive numbers first. So 12 plus 9 is 21. We'll have 21 minus 21, and that's 0. All right, so that says that 3 is a 0 of p of x. That also means that when we go to factor p of x, you're going to see that x minus 3 is a factor. It's x minus 3 times x minus 4. Okay, and then that answers the question, but just to make sure we know what's going on, what is p of 4 going to equal? P of 4 will have to equal 0, right? Because x minus 4 is a factor of p of x. Okay, another example. Here it says, show that the given values of c are zeros of p of x, and then find all the other zeros. So we're going to do number 59 here. What's kind of neat about this is that this thing has degree 3. When we first started this section, I'd mentioned the quadratic formula, which is useful for solving quadratics, of course, and degree 2. This thing has degree 3, though. So we're going to see how we can use the factor theorem to help us solve this equation or find the zeros of this function. All right, so it says show that this value is a 0 of p of x. Now, one way we could do this is by substituting it in, and I'll leave it to you to do that directly. You can plug 3 into p and get 0. That's going to show that it's a 0 by definition. But recall from the factor theorem that this thing is going to be a 0 if and only if x minus 3 is a factor. So if that's a factor, then when I divide by x minus 3, we should end up getting 0 for a remainder. So let's go ahead and divide by x minus 3. 1x cubed minus 1x squared minus 11x's plus 15. That 1 will drop straight down. Okay, so now repeatedly multiplying and adding. 3 times 1 is 3. Negative 1 plus 3 is 2. 3 times 2 is 6. Negative 11 plus 6 is negative 5. 3 times negative 5, negative 15. And then, of course, 15 plus negative 15 is equal to 0. So we knew that already because we know that p of 3 is 3 is a 0 of p. So the remainder had to come out as 0. But what's good about this is that because we divided by x minus 3, what's left here, x squared plus 2x minus 5, that is the other factor of p of x. So we've partially factored p of x. It is going to be x minus 3, x squared plus 2x minus 5. Okay, so we've partially factored p of x. We want to continue finding factors for this thing. Fortunately, the second factor here has degree 2, and so we're able to use the quadratic formula to help find the remaining zeros. So we'll take and set that other factor equal to 0. And then we can use the quadratic formula to help find those remaining zeros. That was our direction. We're going to find all the other zeros. So there's only 2 left. So let's see what we've got using the quadratic formula. So you could also use completing the square if you want to, but quadratic formula is really mechanical. A lot of people like it, so we'll go with that. So we have minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. So that's negative 2 plus or minus. And then in here, this is 4 times 5 is 20 plus 4, 24. So we have the square root of 24, that's over 2. We're going to need to simplify that square root of 24. So there's going to be a factor of 4 in there. And so that will come outside as a 2. So 2 square roots of 6. Finally, negative 1 plus or minus square root 6. All right, so there's all the zeros then. 3, the one that we were given in the first place, negative 1 minus square root 6, and negative 1 plus square root 6. All right, so there's our zeros. And that's the end of the question. So we saw that the factor theorem tells us the relationship between the zeros of a function and its factors. If you remember that the zeros of a function are closely related to its x-intercepts, then that can help us produce the formula for a function if we know what its graph looks like, including the intercepts. So let's try that. So here it says, write the formula for the function whose graph is shown. So this thing has degree 4. Okay, thinking about what we know about n behavior for this, the fact that that's degree 4 is consistent with it having both n's going in the same direction. It has x-intercepts. It looks like at negative 2 and 1. So that means since negative 2 is a 0, it would have to have x plus 2 as a factor. Since 1 is a 0, that means that x minus 1 has to be a factor. Okay, and it doesn't look like there are any other factors. So in order to get the degree to be 4, right now if we stopped here and just multiplied, we'd have degree 2. In order to get the degree to be 4, we're going to need to square both of those. That way, the sum of the degrees is 4, so degree 4, and our zeros are going to be negative 2 and 1, and both have multiplicity 2, which is why the graph will bounce off of the x-axis at those places. So the last thing to do is just to make sure that our y-intercept is okay. So if you substitute 0 in here, let's call this our f right now. If you put 0 in here, you'll have 0 plus 2 is 2, 2 squared is 4, and then 0 minus 1 is negative 1, squared is just a 1. We should have 4. So on the graph, is it true that f of 0 is 4? And yes, it is. So that looks like it will do it. All right, so for this one, we knew what the intercepts were like, and so we used those to write down the factored form. Because if you know the intercepts, you know the zeros, and if you know the zeros, you know what the factors are. Okay, all right, let's try this one. This one has degree 3, which makes sense because the n behavior is one side up, one side down. Since it's degree 3, it ought to have 3 zeros, possibly kind of repeats, but looking at it, it looks like it has 1, 2, 3 different x-intercepts, and the graph passes through the x-axis at those places. So it's going to have a 0 of negative 1, and 1 and 2. Okay, so then it looks like our function should be, well, if negative 1 is a 0, x plus 1 should be a factor. If 1 is a 0, x minus 1 will be a factor. And if 2 is a 0, then x minus 2 will be a factor. So then let's check and make sure that f of 0 is 2, so that the y-intercept is correct. So f of 0, using the formulation shown here, would give us 1 times -1 times -2. And that's positive 2, which is what we needed. All right, so this is our final f of x. Probably a nice idea to go ahead and multiply it out. We didn't do it for our last one, but we can multiply out this one. So taking the first two, we'll have x squared minus 1, and then that's multiplied by x minus 2. And so this will give us x cubed minus 2x squared minus x plus 2. All right, there's our f of x all multiplied out. Okay. All right, couple more examples. So here we're given an f. We want to find f of 2 and then factor f completely. So we're going to find f of 2 using the remainder theorem. So we're dividing by x minus 2. So there's 1x cubed, 2x squared, negative 3x minus 10. Okay, so then we're dividing, so multiply and add. So 2 times 1 is 2, 2 plus 2 is 4, 2 times 4 is 8, negative 3 plus 8 is 5, 2 times 5 is 10, negative 10 plus 10, 0. All right, so we've partially factored f of x. If you know that f of 2 is 0, right, the remainder came out 0, so that's f of 2 according to the remainder theorem. Since f of 2 is equal to 0, x minus 2 is a factor. That's the factor theorem. So far we've partially factored our f. It's x minus 2. That's multiplied by x squared plus 4x plus 5. Which we're reading again that off of the quotient row in our synthetic division problem. All right, so we want to factor f completely. So then the last thing to do is to see, okay, well, can we find solutions of this or roots of this x squared plus 4x plus 5? So we're going to set that equal to 0 again. And then we could try to use a quadratic formula to help us solve this. So let's go ahead and do that. All right, so going through the quadratic formula, we end up with a square root of -4 in here. So this thing is going to have two complex zeros. We'll work with complex zeros more later in this section. But for now, that's enough for us to say, you know what, that f is not going to factor any more than we've already done. Okay. All right, so this question's kind of fun. We're going the other direction. We want to create a polynomial this time. We want it to have degree 4, and we want it to have zeros of -2, 0, 2, and 4. So if we know what the zeros are, then we know what the factors have to be, right? So if -2 and 2 are zeros, then x plus 2, x minus 2 have to be factors. If 0 is a 0, then x is a factor. If you like, if it makes you feel better, write x minus 0. Okay, that fits the format of the other ones. And then finally 4, that will be x minus 4. Okay, so let's go ahead and multiply that out. We fit the requirements though that it has the correct zeros. So starting to multiply this out, we'll have x squared minus 4. This x I'm going to distribute into the x minus 4. So this will be x squared minus 4x. Okay, and then finally we'll multiply that out. We'll have x to the 4th power minus 4x cubed minus 4x squared plus 16x. All right, so there's our degree 4 polynomial that has zeros of plus and minus 2, 0, and 4. Okay, so that takes us to the end of that problem, and we will go ahead and stop this video here so it's not too long. In the next video, we'll continue working on this section and continue doing some more examples.